Good afternoon all. In today's session we are going to discuss about a topic on searching. So searching operation involves the searching of an element in a given list of elements. For example, if you have a list of elements and within those list of elements, if I want to find one element whether it is present in the list or not, then we are going to perform an operation which is called as the search operation. So the searching algorithms, we have many searching algorithms, out of which we will be discussing about two search operations. One is the linear search and the second one is the binary search. So if you look at the term linear search, it is giving an idea that it is a search that is being done linearly. Linearly means we know the meaning of linearity, that means sequentially. So when you are going to search for an element in a sequential fashion, that means one after the other, such type of search operation is called as the linear search. And coming to the binary search, by looking at this name, you can identify that this is a search operation where it involves the division. By means 2, right? So it will be dividing the given list of elements into two halves. We'll discuss about the process, how it is going to follow. We'll discuss with an example how the linear search is going to be performed, and we'll also discuss how the binary search is going to be performed. But before that, just have an idea. The binary search divides the given list of elements into two halves, and it will perform the search operation either in one of the half. That means, for example, if the given list of elements is divided into two parts, for the next iteration it is going to search either a left part or it can search for a right part. When it is going to search in only one part, the remaining part will be completely skipped from the searching process for further searching also. So for each and every iteration, what happens here is we are going to eliminate half of the elements. For example, if you take 100 elements initially that are present in the list, for the first iteration it will divide it into 50 and 50 elements. This is just a vague example I am giving. And based upon some conditions, either it can restrict its search operation either in the left part or in the right part. For example, let us say that it is going to search in the right part. So completely it will avoid the 50 elements from the search operation. Similarly, for the remaining iterations or for further iterations, these 50 elements are divided into two parts. This is 25 and this is 25. Assume that the next operation is going to be performed in the left part. So these 25 elements in the right part will be completely eliminated. So for each and every operation or for each and every iteration, you can see here that the binary search is clearly skipping half of the elements. It is going to perform its operation only in the half elements. Thereby, what happens in this binary search is the binary search operation performs better than the linear search. We'll give it with an example also, don't worry. But at present, you just remember the word that binary search performs better than linear search. We have other search operations like the Fibonacci search, but we are not going to discuss about it. So you just remember these two search operations. One is the linear search, the second one is the binary search. Which one performs better means undoubtedly you can say that the binary search performs better than the linear search. So let us go into the things. What is this searching algorithm? A searching algorithm is a method of identifying or locating a specific item. This item can be an element, or it can be some information, or it can be a data, anything. So a search algorithm is a method of identifying a specific element in a large collection of data. So you will be having a large list of elements, out of which you will be asked to find one particular element. You will be asked to find whether that element is present in the given list or not. Right. After this, as I told that we have two searching algorithms, and coming to the efficiency of search algorithms, in the previous discussions we discussed that the efficiency of the algorithm or the efficiency of the data structure will be measured in terms of the time complexity. In general, we have two terms that is used for the calculating the efficiency of the algorithm. One is the time complexity, and the second one is the space complexity. The time complexity of an algorithm is the total time taken by the algorithm to execute it. And the space complexity refers to the total amount of space that the algorithm takes is called as space complexity. Out of these two terms, which gives the efficiency of any algorithm. So if you want to find whether an algorithm is performing well or not when compared to that of the other algorithm, you will definitely go with these two terms. Either you will calculate the time complexity of both the algorithms, and you will check which one is going to execute in very less time. That is to be considered as the efficient algorithm. Or else you can also go for the other parameter also, that is the space complexity. So you will identify, you will take those two programs and check what is the total space occupied by those two programs, and then you will consider that program which is occupying less memory as the efficient algorithm. So both the time complexity or the time taken should be less. Similarly, the space that is occupied should be less. You can take any of these parameters, but out of these two parameters, if you ask a question whether which one need to be considered well, the answer to that question is the time complexity always plays very important role when compared to that of the space complexity. The reason is the total amount of space that is occupied by the algorithm has nothing to do. Why? Because we have in the present generation, we have lot of memory that is available for very cheaper costs. So you have 1 terabyte of data that is available for just 4,000 or 5,000. So there is nothing, or you can take the primary memory also. Previously we used to have the costs of the primary memory is very high, but right now you are getting the 16 GB of RAM for just 8,000 or something like that. The space that is available in a computer system is very large, and it is available for very cheaper costs. That is the reason why whatever space you take, the algorithm takes, we are not much bothered about it. But the time complexity means it depends on the processor. It depends on how many cores of processor you are having. Whether you are working on a quad core processor or whether you are working on a octa core processor, it also influences. So there are so many factors that influence the time complexity, but anyhow the time taken by the algorithm to complete its execution plays very important role. So out of these two parameters, please consider that time complexity has highest priority than the space complexity. The algorithm which takes less time will be considered as the best algorithm or the efficient algorithm. Similarly, when we come into the search algorithms, in order to find the efficiency of the search algorithm, the efficiency is measured in terms of average time complexity. So if you go for the time complexity term again, we have three different classifications here. One is the best case time complexity. The second one is the average case time complexity. And the last one is worst case time complexity. So any algorithm time complexity can be divided into these three categories: best, average, and third, worst. Again, the same question: what is this best, average, and worst? So the best case analysis means you are going to evaluate the algorithm when you are taking the best suitable conditions for execution. And the worst case analysis is you are going to analyze the algorithm when we have the worst case situations. And coming to the average case analysis, it is the average of all the comparisons. That means you are going to analyze the algorithm and you want to find the average thing, right? So we have different time complexities, and there are different notations for these different analysis parts, but we are not going to discuss about all those things. We are much considered about what is this time complexity and how it is used to measure the efficiency of the algorithm. If you have less time complexity, it is considered to be the less efficient algorithm. And out of this time complexities, you can get these three cases: best case, average case, and worst case. And you may have a doubt again here that whether we need to consider the best case or average case or worst case when you want to evaluate the efficiency of the algorithm. People may think that whenever we analyze a particular algorithm, when we have the best situations, that is to be considered as the efficient analysis, but that is completely wrong. You have to consider the worst case analysis for evaluating the efficiency of the algorithm. The worst case analysis, as we have discussed, that you are going to analyze the algorithm in the worst situations. So in the worst situations, if the algorithm gives best result, then you will consider it as the best algorithm. Even in real life also, you are going to evaluate a particular person whenever he faces the worst situations. So how strong he is or how strong she is, it depends on the worst case situations. So if everything is going right and everything is going according to our wish, so in that case we won't consider to evaluate such type of people, right? So in the similar manner, algorithms are always analyzed, and the main parameter for analysis of the algorithms is the worst case analysis. Here in the search algorithms also, Basically, we will consider the worst case analysis, but more quantified way of finding the efficiency of search algorithms is the average case analysis. So once we have the introduction part related to these search algorithms, let us move our discussion to the first search algorithm, which is the linear search. The linear search, as I told that the search operation will be done in a sequential fashion. So you will search the element, the first element. If it is not matching, you will go with the second element. If it is not matching, you will go with the third element. Like that, you are going to proceed unless you find the search element, or unless you search the entire list of elements. If you find the element, you will simply return the position or the element, or simply you can print a message saying that the element is found in the given list of elements. And if your search operation fails, then you can simply print a message that element not found. This is how the search algorithms work. It is going to give only two messages, whether the search operation is successful or whether the search operation has failed. And coming to this linear search, it is a very simple search algorithm, very simple algorithm, where you will consider a list of elements that are taken inside an array, and then you will start searching the search element from the first element. You compare the search element with the first element. If they are matching, you just return a message saying that element found. If they are not matching, go and search or go and compare the search element with the second element of the array. If they are matching, print a message. If they are not matching, go to the third element and compare it with the search element. This search operation will be continued until you find the search element or you reach the end of the given list of elements. And the algorithm is very simple and it is very easy to code also. This is the first advantage of the linear search. So it uses a simple loop. We know what this loop is. In C programming language, we will use the loop constructs such as for, while, and do while. To sequentially step through an array. So how do you process the array? How do you compare the elements in the array? And if it is not successful, how do you go to the next element? All these things is done in a sequential fashion. And this looping and sequential stepping from one element to another element will start with the first element of the array. This is what we have discussed earlier. So while sequentially stepping from one element to another element, it compares each element, comparison. So this particular operation we are going to do here, comparison. So it compares each element with the value being searched for and stops when that value is found. So when the search operation will stop, in two cases. Either you might have found the element in the given list of elements, or you have reached the end of the array. So when you find the element, you will print the message as successful element found successfully. When you reach the end of the array without finding the element, you will print the message that is an unsuccessful search. Then you will print a message that element not found. Right. Now the advantage and disadvantage of this linear search. The advantage is, we told that it is very simple to understand, it is very easy to implement, and it does not require an array in the order, right? This is very important. This is the main difference between the linear search and the binary search. That is, in the linear search, when you are taking the list of elements for performing the linear search operation, you are not going to take the elements in the sorted order. The elements may be in the unsorted order, but still the linear search algorithm works. So remember that for linear search, you doesn't require the elements to be in the sorted order. Sorted order means already ascending or descending order. And the disadvantage is its inefficiency. Though the algorithm is very simple to understand, though it is very easy to implement, it is not that much good in performance parameter. Performance point of view, this is very inefficient when compared to that of binary search. Right. Why this is very inefficient means, for example, you consider an array of 20,000 items. So my list consists of 20,000 entries. And when you are looking for an element that is present as 19,999th element, it's not this same number. 19,999 means the last element, last but one. Or you can also take 19,998 element. You can take 19,997. The main objective of understanding this particular point is, when your search element is placed as the last element in the array, you need to search through the entire list. So you will be starting your search operation from the first element. If that doesn't match, go to the second element. If that doesn't match, go to the third element, and like that you go on until you find this element. And you know that the element which you want to find is present at as the last element. So the entire list of elements has to be processed here for searching a single element. So if it is present in the first half, or if it is present as the first few elements, if it means the search element. If the search element is present as the first element or the first part of the elements, then it will give good result. But in the reverse case, if the search element is present as the last part of the array, then definitely the efficiency will be very less for this linear search algorithm. That means it is inefficient. So this is all about the introduction part to linear search. And the worst case time for the linear search, as I told, that if you have n records or n elements, the worst case in the sense whatever we have discussed in the earlier case. For example, we will take a short example. Let me take an array consisting of 7 elements. Right. Let me take an example. I have the elements like this: 10, 20, 30, 40, 50, 60 and 70. Let us take the search element as 10. That means the user has inputted the value of 10 and he wants the program to tell whether this 10 is present in the given list or not. Of course, I have taken this as a sorted order, but it may not be the condition, right? You can take the unsorted order also. So to avoid confusion, let me take an unsorted array. So this is my list of elements which consists of 7 entries. And let the user give the the search element as 53. So according to the linear search algorithm, it will take the search element, compare it with the first element. So 53 compared with the first element of the array, that is 53. Since they are matching, you can simply throw a message that element found. So this is called as the best case analysis. The best case analysis for the linear search. That means whatever element you are going to search is present as the first element. So that is considered to be the best case. Now let us see the second case. This is case 1 and case 2. Let me take the search element as 88. For this purpose, you have to compare 88 with the first element 53. Since they are not equal, compare the search element with the next element, that is 88 compared with 26, not equal. Go for the next element, compare 88 with 14, not equal. Go for the next element, 88 compared with 12, not equal. 88 compared with 69, not equal. 79 compared with 88, not equal. And here you can find that 88 compared with 88, and you have found the element. So the message you will get here is element found. But this is the worst case analysis. Why it is considered as the worst case analysis means whatever element you want to find using this linear search, that element is present as the last element. So you need to process the entire list, how many records. In this example, we have taken a very simple list consisting of just 7 elements. But you may have, in real life situation, you may encounter a list which consists of some millions and trillions of records. So the performance of the algorithm will definitely vary in this case. Right. And there is another case. Let me take another case. Case 3. Now let us take the search element as some 93. According to the linear search, compare 93 with first element, not equal. Again compare it with the next element, 93, 26, not equal. Compare with the next element, 93 compared with 14, not equal. 93 compared with 12, like that. It will go through entire list. In the last one, 88 compared with 93. Here also the element is not found. So this is an unsuccessful search. And the message you will get is element not found. So in this case, you didn't find the element in the list. This is also considered to be the worst case scenario. So the worst case scenario is two types. One is if the element which you are going to search is present as the last element. Second one is if the element that you are going to search is not at all present in the given list. So these two are considered to be the worst case scenario. And what about the average case? Average case means you will find the time taken to find the element if it is the first element in the list. So you will find the time here, and you will find the time if the search element is present as the second element, and you will also find time here if the search element is third. Like that, you will take the times taken by all the elements individually. For example, let me take this as x1 millisecond, this is as x2, x3. Like that you consider all the time periods, and when you average those things, x1 plus x2 plus x3 and so on, x7 by 7, this is called as the average case analysis. So in the first slide we have seen that the efficiency of the search algorithm is being calculated by using the average case analysis. That is not a thumb rule. You can also make use of the worst case analysis also, right? And remember that the worst case analysis of the linear search is big O of n. This is a notation for worst case analysis. We will make use of big O notation to represent the worst case scenario. So big O of n means where n represents the number of elements in the given list of elements. So this n is nothing but how many comparisons you are making here. For example, if you consider the 53 case 1, 53 is compared with the first element 53, the element found. So how many comparisons you have made? Only one comparison. So the best case in this case is big O of 1. Let me take case 2 where the search element is 88. So you how many comparisons you are going to do? 88 compared with 53, 88 compared with 26, 14, 12, like that. 1, 2, 3, 4, 5, 6, and the last element, 7th element. Where after comparison only you are going to say whether it is found or not. Therefore, total number of comparisons is 7. So the big O of 7, n is equal to 7. We have total 7 elements as 7 comparisons. So this is the worst case scenario. Like that for case 3 also you are going to perform 7 comparisons, and finally you will not find the element. So for example, let me assume a case where I have 10,000 records. So the n value is 10,000 and the worst case scenario is big O of n. Is it true or not? Right. So to find the element which is present as the last element of the array, it is equal to big O of 10,000. That means 10,000 comparisons. So this is about the complexity of the linear search. And here we have seen that the average case, you take the time taken for each and every element to search the first element, to search the second element, to search the third element, fourth element, like the 10 elements. The array consists of 10 elements, and you average it, we will get the value which is taken as the average case analysis, right? So if you take the formula for this one, this is the time taken for first element search, this is the time taken for searching the second element, and this is the time taken for nth element. So 1 added up to n. So sum of n terms is given by the formula n into n plus 1 by 2, and average means by n you have to do. You cancel these things. So the final result will be n by n plus 1 by 2. So this is equal to big O of n only. So the average case time complexity also evaluates to big O of n. How this n plus 1 by 2 becomes big O of n means there is a lot of theory that is involved in the notations, big O notations, which we are not going to bother about it. But all these constants, so this can be written as 1 by 2 n plus 1, right? Or else you can also be written as n by 2 plus 1 by 2. So you can remove the constant. Constant doesn't have any priority in calculating the notations. And similarly, this n by 2 can be written as half into n. So this can also be removed. So finally you will get the value as n. So that is all about the big O of n complexity. So the worst case analysis for the linear search is big O of n, and the average case analysis is also evaluated to big O of n. Of course, we should not use the big O notation for the average case analysis, but not an issue. And that's all about the linear search. We have seen the process of finding out an element using the linear search. We have seen what the best case analysis is. We have seen what the worst case analysis is and what is the average case. All these things we have seen. So once we are clear about this linear search, let us move towards the discussion on the binary search. As I told that the binary search requires the segmentation of the given list of elements, or the breakup of the given list of elements into two halves. But before that, you should learn some important points regarding this binary search. The first point is it is very efficient than the linear search. We'll see why it is very efficient. And the second and very, very important point regarding the binary search is the given list of elements for which you want to implement the binary search should always be in the sorted order. Sorted order means either you can take the ascending order or you can take the descending order. This is very important. So to implement the binary search, first of all, you have to look for a list of elements which are in the sorted order. For example, if somebody gives you a list of unsorted elements and they are asking you to implement the binary search on those list of elements, the first and foremost point you have to tell is we cannot implement the binary search on the unsorted list of elements. But still they are forcing you to implement the binary search. What you will do is you will simply sort the given list of elements and then you will have to implement the binary search. So for implementing binary search, it is mandatory that the list of elements should be in the sorted order. And this is the process of the binary search. What happens, we will tell it with an example also, don't worry. But if you look at the algorithm of the binary search, the algorithm starts searching the given list of elements with the middle element. So whatever list of elements you have, the first step what you have to do is you have to find the middle element. Middle element of the list. And whatever search element you have, that should be compared with the middle element of the list. If the comparison is unsuccessful, that means the search element and the middle element is not matching, then you have to check whether the search element is less than the middle element or it is greater than the middle element. If the search element is less than the middle element, then you are going to search in the left part only, left part of the array. If the search element is greater than the middle element, you are going to search in the right part only, right part of the array. So if it is less, go to left. If it is more, go to right. This process will be repeated until unless you find the search element or until unless you did not find the search element. Right. So let us discuss this with an example. As an example, let me take a list of elements like this. So I have 7 elements. These are the indices I am representing for the arrays, and let me take first example. Let the search element be 40. So as a first step in the binary search, you have to find the middle element of the given list. So how do you calculate the middle element? You take the first index, you take the last index, and you average it. So 0 plus 6 by 2, that is equal to 3. So whatever element is present here at this index 3, that is considered to be the middle element. So this becomes the middle element. Now let us take the first case where the search element is 40. Compare 40 with 40. Here there is a match, therefore it is a success. You can simply say that the element 40 is present in the given list. This is the best case in the binary search. Now let us take another case of finding the search element. I take the search element as 20. Right. Now you have already found the middle element. The middle element is nothing but the element which is present in the third index, 40. Therefore compare 20 with 40. There is no match. And when you compare 20 with 40, you found that 20 is less than the middle element 40. When you have the less value than the middle value, you have to go for the left part only. That means you are going to search in the left part. So you are going to search in these 3 locations only: 10, 20, 30. And we have this thing. We are not going to bother about this. So you can observe in this particular scenario that you are going to delete almost half of the elements. So in the first iteration you have 7 elements, and in the second elements you are going to perform your search operation in just 3 elements. Right. Here also the situation is not completed. Now what happens? Again you find the middle element within this subarray. How do you calculate the middle element? Take the lowest index, take the highest index, and you find the average. 0 plus 2 by 2, that is equal to 1. So the middle element in this particular scenario is the element which is present under this index 1, which is 20. Now compare this 20 with this middle element. 20 compared with 20, successful. Therefore at this particular position you have done how many comparisons? Number of comparisons is for successful search is 2. Whereas here in this case the number of comparisons is equal to 1. Let me take another case, case 3. And my search element in this particular case is 70. And you take the entire list, you find the middle element. Middle element in the first scenario is which is present at the third index, therefore 40. 70 compared with 40 is greater, 70 is greater. It is not equal, right? Now you compare those values. So the search element 70 is greater than the middle element 40. If the search element is greater than the middle element, you just go to the right part. You skip everything from the left part of the subarray. So you skip this part, this entire part is skipped, and you have only 3 elements here. and the indexes remains the same, 4, 5 and 6. Elimination means you are not going to delete the entire list of elements. You just don't process that array or sub-array. Everything you concentrate on the right part only. Now you calculate the average. That means middle element. 4 plus 6 by 2, that is 10 by 2, that is 5. Now the middle element is equal to 5. I am writing here. So the middle element is equal to 60, that is the element which is present under index 5. Now compare 70 with 60. They are not equal. And you find that the search element 70 is greater than the middle element 60. So what you have to do, you have to go for the right part of the subarray, or the right subarray should be considered. So out of this 50 and 60, the right part is just one element, this one, 70. So the right part is only one element, 70, and it is index 6. Now you have to find the middle part. So the middle is calculated as lowest index is 6 plus highest index is 6 by 2, that is equal to 6. So the element, the middle element is the element which is situated under this index 6, which is 70. Now you compare this search element 70 with middle element 70. They are equal. So you will write it as element found. Simple thing. But how many comparisons you have done here? Is equal to, initially you have made the comparison of 70 with 40, and second one is you have made the comparison of 70 with 60, and finally you have made the comparison with 70 and 70. Therefore total comparisons are 3 here. This one. So for this purpose, let us take, so the number of comparisons in the worst case, that means you are going to find the element which is present as the last element. You have completed the task within just 3 comparisons. If you take the same case in the linear search, if I want to search the element 70, I compare 70 with 10, not equal, go to the next element, 70 compared with 20, not equal, go to the next element, 70 compared with 30. Like that you go on until this particular element is reached. So total number of comparisons is, here I have performed the first comparison, second comparison, third, fourth, fifth, sixth and seventh. So here in the linear search case, finding the element 70 has taken 7 comparisons, whereas the same search by using the linear binary search you have completed with just 3 comparisons. So you can observe the efficiency of the binary search. So here I have taken an example which is having very less elements, a list of elements is very few. But if you consider the large list of elements, the comparison or the efficiency of binary search proves to be very prominent when compared to that of the linear search. So that is the reason why the binary search is much more efficient than the linear search. So worst case complexity is when you want to find the last element. It is equal to big O of log n base 2. You can see here. Right. For example, if we have 8 elements, log 8 base 2 is equal to big O of 3. You can see in the previous case. If you have 7 elements like this, you have made just 3 comparisons. So that is the power of this binary search. So please remember that the average case and the worst case complexities in the binary search is big O of log n base 2. So that's all on this binary search. Let us have the quick recap of what we have discussed in today's session. We have started our discussion with what this searching algorithm is, how many types of searching are there, and then how we are going to calculate the efficiency of search algorithms. We have seen the two parameters that are used to find the efficiency of the algorithm, like the time complexity and space complexity. Time complexity calculates the total time taken by the algorithm to execute, and space complexity refers to the total space occupied by the algorithm. And within the time complexity, we have seen three different cases: best, average, and worst case. And we have discussed that the worst case analysis should be considered to find the efficiency of the algorithm. And then we have moved our discussion to the linear search. We have gone through the introduction part of linear search. We have seen the advantage and disadvantage of linear search, and finally we have seen an example scenario of how this linear search is going to perform. One important point regarding this linear search is there is no restriction on the list of elements when you want to perform the linear search. Linear search can be implemented either on the sorted array or on the unsorted array. And coming to, we have seen the average case, what is the worst case, everything we have discussed. And finally, we have gone through the discussion over this binary search, and we have taken an example, and we have evaluated, and we have compared with the linear search, and we have shown how the binary search is more efficient than the linear search. And finally, we have seen the worst and average case analysis of the binary search. That's all for today's session. Thank you one and all for joining the session.